Good morning, everybody. Now, let us go to experiment number 9. The title says to determine fault currents, voltages in a single transmission line system with star delta transformers at a specified location for LG and LLG fault types. So, LG is nothing but line to ground fault, LLG is double line to ground fault. So the concept behind fault analysis already you have studied in your previous semester, power system analysis 1 subject. So here I have just shown line to line fault, double line to ground fault, single line to ground fault, three phase to ground fault, and three phase fault. Different types of fault have been just shown over here. Basically, this comes under unsymmetrical faults. Generally, we have symmetrical and unsymmetrical faults. As a part of your curriculum in your lab, you will be doing the simulation for line to ground fault and double line to ground fault in single transmission line system. So this will be carried out by simulation and there won't be any analysis over here. Let us take a sample system. We will build the sample system in simulation. We shall run the simulation, observe the waveforms, and nature of waveforms will tell us how to identify line to line fault, line to ground fault, and then double line to ground fault. So let us consider the sample system now. So this is the sample system single line diagram. So let us go through the statement. Determine fault current and voltages in single transmission line system with star data transformers at a specified location for LG, LLG, and also line to line fault for the given power system. Base MVA 100. Simulate for a sample system with the time 50 microseconds and assume the base voltage to be 11,000 volts or 11 kV. So here if you go through the system, we have a generator of rating 18 MVA 11 kV and the internal reactance is 1.2 ohms and you are having a bus bar here and from the generator bus bar it is connected to a step up transformer of connection configuration delta star, delta in primary, star on the secondary, neutral grounded. Its rating is 18 MVA 11.5 slash 34.5 kV and the reactance is 10% and we are having a transmission line connecting the two transformers. The positive sequence reactance of the transmission line is 2.497 ohms and negative sequence reactance is 4.995 ohms. And similarly, the rating of the second transformer is 15 MVA 34.5 by 6.9 kV and reactance is 10%. And at the load end, we are having a bus bar to which the load is connected and the reactance of the load happens to be 0.6347 as the positive sequence reactance and zero sequence reactance 0.03173 ohms. And other than this, the fault resistance to be taken is 0.01 ohm and the resistance is 0.001 ohms. So this system has to be simulated using simulation package called Simulink and then the waveforms will be observed and the after observing the waveforms comments must be given. So let us go back to the procedure. So coming to the faults here. So in order to build this system, first we connect a three-phase source from the power system simulation block. We are having a power simulation block in simulation window in Simulink. We just pick three-phase source from there. And then here we have three-phase VI measurement. We are having another block called scope. We have multimeter, three-phase transformer, three-phase pi section line, another three-phase pi section line, three-phase fault, and we have another three-phase VI measurement block. Then we have three-phase transformer, two winding. Then in order to simulate the load, we have taken three-phase mutual inductance Z1, Z0. So here we'll have to pick all these components that I have told just now from the library. So after picking them from the library, as per the single line diagram, source will be connected to a transformer, which is step up transformer. In between we are having a transmission line section, and on the other side we have another transformer followed by load. And here in between, for measurement purpose, we have connected three-phase VI measurement block, which will give us the voltage in all the three phases, and it will also give us current in all the three lines. So for measuring that, we have this three-phase VI measurement block. Then here we have three-phase pi section transmission line. The transmission line length is known to us. So we take half of the transmission line modeled over here, the other half of the transmission line modeled over here. Say for example, if the transmission line length, see if the transmission line length basically, just a minute. Yeah, in this particular example, the transmission line length happens to be 1 kilometer. So half a kilometer of transmission line is modeled using one block, another half kilometer is modeled using another block here, and the fault is set to take place in the middle part of the transmission line. At the center of the transmission line, the fault is taking place. So we are simulating three-phase fault in between the transmission line. We have 0.5 kilometer of transmission line represented by this model on the left side, and other 0.5 kilometer on the right side. In between, we are having three-phase fault block. So this will be connected to all the three lines. And then again we are having another three-phase VI measurement block over here, again for the measurement of voltages and currents VABC and IABC. Then we are having a transformer block, as usual, step up or step down transformer, and you'll have to double click on this block to configure either star connectivity or delta connectivity. And you are having three-phase mutual inductance acting as a load. On the other side it is grounded. Then we use a multimeter here, which will give us the fault measurement readings. So in the three-phase fault block, we are going to configure this particular block, and there we are going to declare which all parameters has to be measured. So whatever will be declared will be connected to this multimeter, and here you can see in multimeter it reads 6. So we have opted for 6 measurements, so that will be displayed here, and the graph will be displayed automatically. Apart from this, you can wire a small network, and you can wire this particular VABC to scope 1. Scope 1 will generate the graph of VABC since it is connected to VABC, and there is another scope to read VABC on the load side. So scope will generally display the graph to which it is connected to. Here we have VABC connected on load end, another VABC on the supply end. And here you can see discrete power GUI. This shows us the simulation configuration, whether you are going for continuous time simulation or discrete time simulation. Here generally we go for discrete time simulation, and from the sample system we were supposed to do it for 50 microseconds. That will be configured over here in this particular block. Now let us see what are the parameters we'll have to key in as per the given problem. From the given ratings of the machine, we are going to key in the following parameters. So first block is three-phase source block. What all you have to do is double click on this three-phase source block. This first screen, whatever you are seeing on the leftmost side, will open. Here first you are going to enter face-to-face RMS voltage is 11 kV as per the given data, frequency 50 Hz, internal connection star grounded, and here source inductance 3.8514 into 10 power minus 3. Reactance is given. You have to convert it into inductance. XL is 2 pi FL. L will be equal to XL by 2 pi F. Using that, you will be getting the source inductance. Then base voltage is to be considered as 11 kV as per the given data. So this finishes the modeling of three-phase source. Next you have three-phase transformer, two windings. So here nominal power is given in the rating of the machine in the problem, which is 18 megawatts, frequency 50 hertz, winding 1 parameters 11.5 into 10 power 3, 11.5 kV, and we are not going to change R1 and L1. We'll be retaining as it is the default values. Winding 2 voltage is 34.5 into 10 power 3, 34.5 kilovolts. That will be there. And then R2 and the L2 we will retain default values that is there in the software. Magnetization resistance and magnetization reactance also will be retained with the default values, because we are not going for detailed modeling of the block. We are not going to change that. We are just going to change the functional parameters, which are winding 1 voltage, winding 2 voltage. We are not modeling the block as it is. Then coming to the three-phase pi section transmission line. This is configuring the transmission line. Again, as what I told, as how I told for the first block, here also you are going to double click the transmission line to invoke this window. Frequency is 50 hertz. Positive and zero sequence reactance are zeros. Sorry, positive and zero sequence resistances are zeros. Inductances, reactances are given. Convert them into inductance and enter the values. 7.95 into 10 power minus 3, 0.0159. You will be getting that. X1 and X0 are given in the problem. Convert them back to inductances and enter them here. Then line length happens to be 0.5 kilometers. Let us go to the next part. So in the next part, you are having modeling of the other transmission line. So again, same values will be there as per the previous case. Same thing has to be entered. Next, we'll go to three-phase fault block. So here in this window, you can see phase A, phase B, phase C fault. Here you are having a provision to enter fault resistance, which is given in the problem 0.01, and then grounding resistance RG is given in the problem 0.001. The transition status says 1 0. Transition state, that is initially it will be on, then it will be turned off. It will be a indication given to the relay to turn off during the once the fault is applied. The breaker will be given a signal to break the circuit. Then here it says transition time 3 by 50, 5 by 50. This means the fault is set to occur between third and fifth cycle of the input. That is, we are manually creating the fault. So we have the choice of creating the fault at a particular location in the waveform. So we are creating the fault between third and fifth cycle. Likewise, it can be changed. Then snubber resistance, snubber capacitance will leave the default values. Then coming to the next block, you are having the second three-phase transformer and nominal power, which is given in the problem 15 megawatts, 50 hertz, and then winding 1 parameters 34.5 kilovolts, and then R1 and L1 default values, winding 2 parameters 6.9 kV, and then again here also R2 and L2 are default values. Resistance and magnetization resistance and inductance are also default values. Default in the sense, whenever you double click on the block, whatever values are there in the software, by default you leave it as it is. Then coming to the last block, three-phase mutual inductance block Z1, Z0. Here also reactances are mentioned in the problem. Convert them to inductance and enter the values. 2.0206 E minus 3, 1.0103 E minus 3. So enter all these values, just say OK. And simulation solver that we are going to use here is Power GUI discrete simulation. Sample time that you have to configure on Power GUI block is 50 microseconds, 50 hertz. Base power as per the given data 100 megawatts. So this has to be built, and please run the simulation and observe the results. The results resultant waveform, whatever you have to observe, is already discussed in the class in detail. So you just have to observe the waveform and check for the fault currents and voltages. You just have to observe the waveform, what happens to the VABC and IABC voltage waveforms and current waveforms during the short circuit condition for different types of faults, say line to ground, and then double line to ground. Whenever you are configuring the faults, here in this block you can see phase A fault, phase B fault, phase C fault, and you are having ground fault. In case you want to go for line to ground fault, you'll have to tick the option phase A and ground, or phase B and ground, or phase C and ground. Any one of the line you have to check, and then ground. Double line means you have to select two lines here and one ground. If you want line to line, uncheck this ground, go for any of the two lines, and then the fault will be simulated. And please observe the waveform and check whether it is same as the theoretical waveform. Theoretical in the sense whatever waveform we studied during the uh, explanation of the concept, whether it is the same or not, and try to comment on the results. This finishes the last experiment, experiment number 9.